Rivet 29C.
So what is forgot this week? You know?
I don't know. I'm not sure. We left. Oh, that's right. We didn't get to this. Yeah. All right, let's wrap this up, and then we'll do another capacitor problem from one of the old tests, and sort of see where we stand on those capacitor circuits. We have one more little topic, capacitors, to deal with. All right. Do you feel like you need more practice on the capacitor circuits? Yeah, I think you do. All right. So let's try this. What is the equivalent capacitance of this? So, you might be able to do it in your head, or you might want to sketch it out.
We're just assuming C is just
C is
random
just,
number.
it's just a number, right? But
But they're all the same.
they're all the same, right?
Mm-hmm.
About 10 more seconds. 1:35. A few more seconds. That's everybody. 1 to the 5, 7. Alright. Let's see. Most of you put B. There are a couple things that are, I'm going to assume it's B. I don't know what it is right off. But first thing, you just want to think about how this circuit is and which part do you want to attack first. That's going to be this part, because these two capacitors are what? Series or parallel? Those two are in series. So if I redraw it like this, it might look like a little more sense to you. That's the same circuit. Alright, so these two have capacitance C, and so I can find the equivalent of those two is 1 over C plus 1 over C. It's going to be 2 over C, the inverse, C over 2. And then I... is that right? Yeah, so A is the right answer. Yeah. You can't always follow the crowd, can you? Alright, so if that's C over 2, this is C, and then I combine this capacitor with that capacitor, so it's going to be C plus C over 2, which is equal to 3/2 C. Let's see, what did y'all do to get B? I don't know what you did to get B. You did the ones in parallel? Yeah. So you did a 2C with C in parallel? Okay, yeah, that's not correct. You can always tell if things are in series because, see, notice here, even though they have this bend, there's no split. All right, so you're looking for splits in the wires, and that tells you when you have a parallel circuit. Let's try some more. All right, how does the voltage across the first capacitor compare with that across the second capacitor? V1 to V2. Is it equal, larger, less, or 0? You should be able to just look at that circuit right off and tell me what all the voltages are and what all the charges are. About 10 more seconds. Stop at 55. B is correct. What is the voltage on C1? It's 10.
Oh, C1.
Yeah, C1 is 10 volts. C2 then is what? Right, I have 5 volts here, and C3 is also 5 volts. What are the charges on C1? C1 has a charge. What is it? No, it's going to be 10. So Q is equal to CV. So that's 1 microfarad times 10 volts. So I have 10 microcoulombs. All right, and then on each of these, I have 5 microcoulombs for the same reason. All right, you with me on this? So you'll have some multiple choice questions on your test that are similar to this. I'll give you just a circuit, a simple circuit, and ask you about the distribution of the voltages and what have you. All right, let's see. How does the charge on the first compare to that on the second? I just wrote this if you still have it in front of you. Equal, greater, less, or 0? Q1 to Q2. Now we're going to Q, charge. About 10 more seconds. Stop at 55. All right, B is correct. Right. Let's do 1 or 2 more practice problems with the big capacitor circuits, because that's going to be on your test. We worked through one, but I want to work through another one. You have an example in the back of your book. This is number 16 on exam number 1 in the back. This was a little bit simpler than we worked last time. You might be able to trace it out a little more easily. But the first thing I want you to do is to just draw this circuit out in a more regular way, in the way that we've been doing. Now this isn't homework. This is number 16 in the old exams, exam number 1. You can do this how you like. Usually we start on the big side of the battery and go around the positive side, but you can go the other way too. It's fine. Pause for a minute when you get your circuit drawn. So I just want you to draw out the circuit, not combining any capacitors, just drawing it in a more regular way. What's going to happen to the circuit at this red dot? How many branches is going to split into? It's going to split into 3 branches. Like this. 1, 2, 3. You can imagine, you see how there are no capacitors here? In that, you can reorganize those wires basically as you see fit. So I can imagine that this wire has just disappeared, and I pull this wire down to here. And then that looks more like I have 3 branches. Right? So I can move that down, and then I see 3 branches.
Does it really matter?
It does sort of matter because when we start to simplify the circuit, it'll be easier to see. Because you're going to have first a series combination that you'll combine, and then a parallel combination with 3 capacitors instead of 2. What's on this leftmost branch? Right, that 2 microfarads, C1 is equal to 2 microfarads. The middle one? Right, that's C2, which was 3. And then over here, we have what? 10? Then what else? I have 2 10s, right. Alright. So that's the same capacitor, or same circuit. Now I want you to find the equivalent capacitance of that. If you're not getting this, don't sweat it. We'll do another one after this, and then there's some homeworks too for this. When you get your equivalent capacitance, I want you to click in. Is it 30, 20 over 3, or 10 microfarads? So just when you get that, go ahead and click in. What is your equivalent capacitance? 30, 20 over 3, or 10? What is your equivalent capacitance? A 30, B 20 over 3, or C 10? To remind you that when you're finding the equivalent capacitance of capacitors in series, that it looks like this: 1 over C plus 1 over C. That's for a series. If you finish that, go ahead and start finding the charges and voltages on all the capacitors. Alright, about 15 more seconds. Stop at 3:05. Okay. That was good. B is the right answer. Let me show you. So just pause for a minute. I first combine these two, and that gives me 1 over 10 plus 1 over 10. So that gives me a what? 5, right? So I can redraw this, and I find it useful to redraw the whole circuit. This is 20.
I mean, 1 over 1 is 5.
Yes, 1 over 2/10, which is 5. This is 2 and a 3. This is a 12-volt battery. God bless you. And then what do I attack next? Goodness. The what? Right, that 2, 3, and 5. I just add those up, so that's 10. So those all add up to equal 10. Or 10 microfarads, excuse me, not 10 volts. And so my new circuit will look like this. And then I can combine those two. They're in parallel or series? Those two are in series, so I'll combine them. And the equivalent of those is going to be 1 over 10 plus 1 over 20, which is 2/20ths plus 1/20th, 3/20ths. The inverse is 20/3. All right, so that's our equivalent, yeah, 6.67. All right, now, you should be able to look at this. I'll show you how to work it out, but you should be able to look at it and figure out what are the voltages on the 10 and 20 microfarad capacitor. All right, remember, we have this relationship that Q equals CV. So if C is small, V is big. Remember we had this with the 3 and the 6 microfarad capacitors last time? If I have a small C, I have a big V. All right, so what is the voltage then on the 10 microfarad capacitor? Has a voltage equal to what? Is it
Sorry. I was not looking up whenever you were writing it down.
all right, I think y'all know this. It's 8 volts, right? And this has to be 4 volts. The reason is that the voltage across the 10 microfarad capacitor is twice that of the 20 microfarad.
Again, I'm sorry. I thought it was a group, like, kind of.
Right. Right. I always say that like somebody can just stand up and shout out the answer, but nobody ever does. Okay?
Well, I guess there's a first time for
Right. So you can start filling in your table. That 20 microfarad, that was C5, so it's 4 volts right here. Now look guys, that was easy because your numbers are easy, right? And I try to give you easy numbers, but in the case that you don't have easy numbers, what would you do there? Huh? No, like let's say they're just decimal numbers, and there's no even distribution. It's like a factor of 3.45 or whatever, and the numbers you can't really do in your head. How would I calculate the voltages on those? What would I first need to find? I would find Q equivalent. So find Q equivalent here. It's going to be 12 times 20 thirds CV. Well, let's see, it's 240, that's 80, right? Is that right? No, it should just be 80. 240 over 3. Right, it's 80. Yeah, so it's 80 microcoulombs. And then you know that both of these have 80 microcoulombs and 80 microcoulombs. And then now that you know Q, you can work backwards and find V, right? By this Q equals CV relationship. So that also gives us Q5, 80 microcoulombs. All right, try to find the others. I'll give you a bit. The 80 microcoulombs is the equivalent charge. That's the charge on this 20 thirds microfarad capacitor. But one of our rules is that caps in series have the same charge. And then we had another sort of sub-rule, which I think we called it like 1A. And that charge is the same as the equivalent capacitor. So if this capacitor has 80 microcoulombs, then both of these capacitors, which are in series, also have 80 microcoulombs. Does that answer your question? Oh, how did I calculate 80 microcoulombs? Is equal to CV, and that's going to be 20 thirds microfarads times 12 volts, and that's equal to 80. Sorry, I didn't realize your question was so simple. All right. You should be able to fill in some other numbers just from this data that we have, because things start to fall into place here. What is V1? What's V1? 8 volts, right. Because I have 8 volts across this capacitor, that means I have 8 volts on each of these capacitors. Because they're in parallel, and caps in parallel have the same, what is it? Voltage, right. They have the same voltage. So capacitors in parallel have the same voltage. So I have 8 volts. What is V2? 8 volts. What's V3?
4.
Very good. And V4? All right. The reason that V3 and V4 are 4 volts is because these capacitors share 8 volts. Right, because this had 8 volts on it. Capacitors in series, their sum of their voltages equals the total voltage. And that's it. And then you go through, and here you know all the voltages, so you can figure out what are all the Qs. I'll leave that to do on your own. That's all right, huh? The hard part's redrawing it, really. Yeah, that takes practice. Well, that's not just the hard part. The hard part is also knowing how to apply those rules. But let's do another. So I think I have a couple other questions. Let's do a couple of these multiple choice questions, I think. Did I have any here? Let's try this number 10. Consider this circuit. What is the voltage across C1? They're all the same. C1, 2, and 3 are all the same. I'll stop at 120, about 8 more seconds. That's not right. It's not 6. I'll try it again. Not 6. Just open it back up
All
again.
of them are so close.
Uh-huh. But it's not C.
We have 3 voices now.
About 10 more seconds. Stop at 45. All right, look. Let me just redraw it. I'll give y'all one more chance, but let me redraw it here. So we have C1, all right, which just has a, I'll just call this actually C. I'm just going to call it C. It has a capacitance C, and then I have another capacitor here which has a capacitance 2C, all right, because I just add them up when they're in parallel, and I have 12 volts. And I want to know what is the voltage across this capacitor. Oh, we just did this problem. What is the voltage across that capacitor? It is either B or D. It's one of those.
Oh, thank you for letting us know.
Yeah. Remember our relationship, Q is equal to CV? And these have the same charge. So the capacitance is different, the voltages are different. Stop at 35, 35. That's right. He's right. We should have that some way on our tests, like where we can have progressive answers. No, that's not right. And like as a class. Good job, 3 of you.
What's the computer test for that probably would kill us from the whatever points you gave us for trying.
What's that?
I said we could probably do computer tests, but that would probably kill the score that we can get from the partial credit.
Yeah. Yeah, I haven't thought of a good solution for that. All right, so we had similarly before, right, where if we have a small capacitor, it has a big voltage. And here we have a capacitor that's half the size, so it has twice the voltage. So I have to have 8 volts here and 4 volts here. If you're looking for some, sort of how are things distributed in circuits. I want to spend a lot of time on it here. I know it seems like we're sort of beating a dead horse, but this will come back when we do resistor circuits, because things are going to be very similar when we deal with the resistor circuits. Y'all started in the lab already, haven't you? Right? And my wife said that y'all were not very happy about it. All right. It is very similar, but a little bit different too. Right. All right. Let's see. I think that was all that had on capacitors on this test. All right. You want to do one more problem? All right. We have to go back to the old test. So this isn't in your book, unfortunately. Look, I've been trying to use Chrome because I hear that people who use Chrome are smarter than people that use Firefox or Explorer. Is that true?
You're really gonna fall into that thing, or into that thing where you just hear something and say, it must be true.
Oh, it must be true. It was on the radio. I heard it on the radio.
Yeah, that's equally as well.
Huh?
Who did the survey? Google Chrome?
Right.
No,
That's kind of like saying those who live in Beverly Hills will be smarter than those who live in Florida.
Yeah.
Actually, I think there's a thing called Google Stack. That was probably where it came from.
Let's try this one. Okay. And then we'll do another one. What is the equivalent capacitance of this circuit?
So, what test is that?
Oh, this is spring 12, exam 1. Hopefully you can just look at this and do it really quickly.
20 seconds.
They're easy numbers. They're numbers that we've seen before. 3 and 6 in series gives you what?
Okay.
Watch. We're gonna have to do it 3 more times because we all get it.
Right. Well, this is supposed to be easy.
Apparently not. Idiot, bro.
It's
Apparently.
right now.
That's fine. You can write it down.
It's easy for teaching that stuff too. We should have
It's difficult as a teacher because as you teach a topic many years in a row, like you get better at it, as you should, right? But you forget that your students, it's their first time to ever see it for many of them. And so you expect them to be better at it too, but they're not really. They're just seeing it.
It's kind of our organic teacher is like, you see obviously. Obviously. Just obviously.
All right, 135. Who is that, Satula? I like him. He is like the cutest little baby. Like, I don't usually think the babies are cute. But you gotta see his baby. Y'all seen his baby? It's like the cutest little baby. Very, very good. B is right. Alright, well, let's get down to a real problem.
A real
I guess it's
problem.
not just unanimous.
That wasn't real? Oh, no, it's just, wow.
Hey, this is a good one. Let's try this
Same
one.
we've already done.
Oh.
Have we done this one?
I think, at least at one point.
No.
No, it is a little bit different, I think.
It is.
Maybe
There's 2 boxes.
Oh, it's not the day.
Is it the same as the one?
Like a month longer or something, similar to this.
It is similar, but not quite. It is the same thing. Yeah, it's exactly.
On what page?
This 9.
Oh, yeah. Yeah, let's go to another one then. I'm sorry.
Time clocks. I already forgot that they're done.
Let's go to spring 11.
Looks like yours like 3 days ago.
I do change the circuits up. Yeah, let's do this one. So first just find the equivalent capacitance, or first redraw it. These are nice, easy numbers, okay? So when you get good at this, you should just be able to look at it without really drawing it at all. The equivalent capacitance first. I haven't opened it up yet. Right, you can go ahead now.
Should I stand up and scream?
No. So when you get the equivalent capacitance, please click it in. And if you've already found it, you can go and find all the charges and voltages on all the capacitors. I'm going to stop this at about 3:05, 10 more seconds. So if you don't know the equivalent capacitance, just go ahead and click in guess. 5 more seconds. Got everybody. All right, B. That's right. Good. So, as I said, sort of the tricky part is redrawing it. I think we've had one very similar to this. It looks like this. I have 2 capacitors. After this point, it breaks into 2 branches. And so it's like I have a parallel branch within the parallel branch. And then it all comes back together and goes back to the battery. So I have a 2 and a 2 right here. And then the first one that you take apart is this one. A 2 and a 2 gives me a 4. And then, I'm just going to skip a step here, but a 4 and a 4 gives me what? A 2. All right, maybe I won't skip this. Let me go ahead and draw it out. So I have a 12, 6, 4, 4, 1, and then I combine that 4 and 4, which gives me 2 microfarads. So I have a 2 and a 1. So that's 6 microfarads, 2 microfarads, and 1 microfarad. 2 and 1 give me what? 3. And then 3 and 6 in series gives me a 2. So I'll come up here. I have a 6 and a 3. And that gives me 2 microfarads. Easy or no? Yeah, this will be our last example, though there are other practice problems that you can do in the old test. If you go back, practically every test has a circuit like this. All right, and now I want to start stepping back. I always find it, as I said, useful to draw out my circuits like this. It helps me when I'm trying to figure out what are the voltages. If I have 12 volts there, again, you could find the equivalent charge. The equivalent charge would be, what is it? 24 microcoulombs. That's just C times V, 2 times 12. And then that charge is on the 6 and the 3 microfarad. Right? Or you can just look at it and you can say the 3 microfarad has what voltage? What voltage on the 3 microfarad? Right, there's 8 volts. The smaller capacitor carries the higher voltage. And then this has to be 4 volts in order to add up to 12 volts. Still with me on this, folks? Yep. It's 20 points on your test, so it's not insubstantial. All right, so we can start filling in some things. Let's see that 6 microfarad with C1. So that's going to be 4 volts, and we had 24 microcoulombs. Now we have on this capacitor, what voltage? That 1 microfarad is C3. What's our voltage on that capacitor?
8 volts.
8 volts. Because that capacitor is part of this equivalent capacitor, and capacitors in parallel have the same voltage. So that was C3. It's going to be 8 volts. This capacitor has what? Has 4 volts on it. Right. We know that these 2 capacitors combined have 8 volts because this capacitor had 8 volts, and so we know that those split that 4 volts. So that 4 volt capacitor was 4 microfarad capacitor is C2, so it's 4 volts, which is going to give it 16 microcoulombs. And C3, which was 1 microfarad, will have 8 microcoulombs. I'm just doing C times V here to get the charge. All right, now the only thing left are C4 and C5. What are the voltages across them? Right, so if we step back here, we saw that we had 4 volts across this capacitor right here. but that capacitor is just these two capacitors. Caps in parallel have the same voltage. So we're going to have 4 volts here and here. And then we can also find the charge. 4 times 2 is 8 microcoulombs for both of these. Alrighty? You all good on that? Capacitor circuits. There's one in the homework, and you can find several more in the old exams to practice. One more thing for capacitors before we move on to the next chapter. Can I close out this? And that is energy in capacitors. And we said that capacitors have a couple purposes. You remember the purposes instead? Huh? Right, they hold a charge, right? They can be saved and used for later. Or, in particular, storing energy. Like, what was that example we saw where the guy used the capacitors to store energy? Right, he uses sort of, it's not a battery, right? Because it's a different process from a battery, but it works like a battery, where you're saving energy for later. And that's what a battery does too, but just by a different process. So one of the primary purposes of capacitors is to store energy. Do y'all remember the other purpose for capacitors? We'll get into this in a couple of chapters. Huh? If you remember in the magazine video when he hooked up the LED to the battery and then he discharged it, or he hooked up the capacitor to the battery, charged the capacitor, then he hooked up the LED to the capacitor, how did the light shine? Did it shine constant? All right, it brightened and then it gradually got dimmer. And so one purpose of capacitors that we'll see in a couple of chapters is that they provide really nice time response for circuits. So anytime you have like a flashing light, like those flashing lights out on the road, those are usually because of capacitors. Because capacitors discharge and charge at a very regular rate, depending upon the capacitance. We'll see that when we get into what we call RC circuits.
Did you know that actually light bulbs because it's alternating current, they actually dim constantly?
At 60 hertz?
On and off and on and off and on and off, and you can only catch it on high speed camera.
Yeah, that is funny. Do you know what happens when a frog's car breaks down? This is funny too. Do you know what happens when a frog's car breaks down? It's towed. I think that was funnier. All right. So energy stored in capacitors. We've already watched this video, actually. That's the one that we watched with Colin, my hero. The energy stored up is given by this expression, 1/2 CV squared. It comes out, it's an integral of something. I forget exactly how you calculate it, but it comes out as 1/2 CV squared. You have a couple of simple homework problems, just asking you to calculate the energy. And I might ask on the test, what is the energy stored in this capacitor, for example. But so here, if we want to know the energy stored on this capacitor, we would have 1/2 times the capacitance. And notice here that I have to convert it all to SI units because my energy is in joules and everything has to be in proper SI units. So 1/2 of 10 microfarads times 2 volts squared, and that's going to be 20 microjoules. 20 microjoules.
So if you had a bunch of capacitors, you would just bring it down to that one capacitor.
If you want to know the total energy, yeah, that's combined. Or I could ask you on an individual capacitor, what's the energy on that capacitor?
So C could have been C's capacitor equivalent.
It could be, yeah. Or it could just be one capacitor hooked up. But I more want you to understand that, capacitors store energy. And this equation, it's on your equation sheet, so it's not a big deal. It'd be just simple. Plug it in.
You're saying to get the overall energy, you have to use the capacitor equivalent?
Yeah, if you want to know the total energy in the circuit, either you can find the equivalent capacitor. Oh, wait, no. No, I don't know, actually. Because if you added up all the capacitors, you'd get a much higher energy than if you just used the equivalent capacitor.
That's what I'm saying. So you have to do one individual, you go over all of them and add them up at the end.
I don't know. I'll have to think about that. Not sure. You understand what he's asking? Robin. So you know, what if I had a circuit? Let's see, this might work out okay. So this would have an equivalent of 2 microfarads. Sorry, this is kind of a rabbit trail. 2 microfarads, so the energy of the equivalent capacitor would be 1/2 of 2 times 10 to the minus 6 times, let's make this 10, okay. No, let's make it 12, times 12 squared. That's 144 times 10 to the minus 6.
Would it be equal to these two equal featuring the things you're using the 12 on?
I don't know, just hang with me for a second. So that's going to be, I'm sorry, this is not terribly relevant. 0.0001, and then .0000048, and then if I just add those up,
You get 0.000148.
right, which is awfully close to this value. I don't know if the equivalent, the energy on the equivalent capacitor is the same. It looks like it's close here.
So if you're doing it on a bunch of capacitors, you would add them up?
I think so. I mean, on the test, yes. But like in real life, that's what you're asking, right?
Yeah.
I think so. I'm not positive. All right. Well, that's the end of chapter 2, guys. We'll pick up chapter 3. Chapter 3 is short. You know, we might get into chapter 4 before the test, but I'm inclined to not do chapter 4 on the test. Y'all too? All right. Y'all have a great day.
You can